Okay, so we are doing the chapter 23, more on analysis. Not the limits, but chapter number 24, my bad. Yet more on analysis. And we are doing the chapter continuity. So we have defined the continuous functions. And then we have talked about that a function is continuous on R if it is continuous at every point in R. Then we have defined the sum, product, and quotient rule for the continuous functions. Then we have defined the intermediate value theorem, and we have given that theorem as that we are saying we have a function which is continuous on R, and let there are two variables, two values in from R, A and B, with the condition that A is less than B. Then we are saying f of A and f of B are not equal. Then for any real number gamma between the f of A and f of B, there exists a real number C between A and B such that f of C is going to be gamma. And we have proved this theorem. It's a long proof, but it's a very good one. Now we are going to talk about the existence of nth roots. So we have worked on the nth roots before. Now we are going to show the existence. So our first application of the intermediate value theorem is to prove the existence of nth roots of positive real numbers. Stated long ago is proposition 5.1. So in proposition 5.1, we have said that there exist nth roots. Now we will prove them using the intermediate value theorem, prove their existence. So we have a proposition. (24.2), and the proposition says that let n be a positive integer if d is a positive integer, positive real number, then there is exactly one positive real number C such that C power n is going to be D. Okay, let's give the proof. So let's define a function f from real numbers to real numbers with the equation x power n minus D. Now then, f is a polynomial function, and hence is continuous on R? Every polynomial function is continuous on R? Now, let's say f of 0 is going to be d, sorry, minus d, which is less than 0. Also, if we choose b to be the real number, b a real number, such that b is greater than the maximum of 1 and d, then f of b is going to be b power n minus d, which is greater than 0. Hence, f of 0 is less than 0, and it is 0 is less than f of b by the intermediate value theorem. There is a real number c. C between 0 and b such that f of c is 0, which is to say that c power n minus d is 0. So c power n is going to be d. This proves the existence of c. Thus, the uniqueness is easy. We suppose that c power n is c1 power n, which is d, with the condition that c1 is less than 0, sorry, greater than 0. Now, if c1 is greater than c, then we will have c1 power n greater than c power n, and if c1 is less than c, then c1 power n is less than c power n. Now, neither of these is possible. So, c1 is c, proving the uniqueness. of C. So this shows that there exist the nth roots of nth roots. Okay, perfect. Now we will give the special case of the fundamental theorem of algebra. Now remember, the fundamental theorem of algebra stated is theorem 7.1 says that every polynomial equation of degree at least 1 has a root in C. In the set of complex numbers, this is quite a sophisticated result whose proof you will probably have to wait to see until you take a course on complex analysis. However, there is a really neat proof that works for real polynomials of odd degree and use just the intermediate value theorem. So let's give that. So we have a proposition. And this is going to be the last proposition of the chapter and the book. So we are saying let P of X be a polynomial in X of odd degree with real coefficients then the equation P of X is 0 has a root, has a real root actually. Okay. Now let's prove this theorem, this proposition. So we are saying let P of X is the polynomial an x power n plus plus a1x plus a naught with an naught 0 and n is odd. We may as well assume that the an is greater than 0, or we have to replace P of X with minus P of X, which has the same proof. Let's write that. Otherwise, replace P of x with minus P of x, which has the same proof. But now we have assumed, so we don't need to replace it. Now for large positive x, the value of P of x is dominated by the leading term an x power n. So there is a positive real number p such that p of p is greater than 0. Similarly, so the above point is this this needs some work, but the details are easily filled in, and you can try that yourself. So similarly, for large negative x, the dominant term is also an x power n, which is now negative because n is odd. So there is a negative real number a such that p of a is less than 0. Thus, p of p of a is less than 0 and 0 is less than p of p. Okay. Now, p of x is a continuous function. So, by the intermediate value theorem, there is a real number C between A and B such that P of C is 0, then C is a root of P of X is required. And this proves the theorem. I hope you like this argument. If you do, you are undoubtedly a budding pure mathematician. And even if you do not, you may well find lots of other branches of pure mathematics to tackle your fancy. Good luck in your future studies. It's really hard to think of a better place to stop, so I will stop here. Thank you for being part of the journey of reading this book, learning this material. We have almost covered small 24 chapters of the basics in the pure mathematics. Thank you so much.